Welcome! In this revision guide, we're going to tackle a process that seems almost like magic, using electricity to split chemical compounds back into their original elements. It's called electrolysis, it's a huge part of the AQS specification, and you know what? We're about to make it really simple.
So, let's just start with a puzzle. Imagine you've got a compound, something like lead bromide. It's pretty stable. How on earth could you force it apart to get that lead metal back? It sounds kind of impossible, right? But the answer is a process that uses the power of electricity.
So here's our game plan. We'll kick things off with the key definitions you absolutely have to know. Then we'll see electrolysis in action, first with molten stuff and then on a massive industrial scale. After that, we'll get into the slightly trickier rules for solutions, and finally, for those of you aiming for the top grades, we'll cover half equations.
Okay, let's dive right in. Part 1. What is electrolysis? Seriously, getting the language right here is the foundation for everything else, so let's lock in these key terms.
So at its heart, electrolysis is basically a decomposition reaction, and the name itself is a massive clue. Electro for electricity, and lysis, which is just Greek for to split. So we are literally using electricity to split a compound into the elements it's made from. Simple as that. Now, for this to work, the electricity needs something to actually flow through, and that's our electrolyte. But here's the crucial bit. An electrolyte isn't just any old ionic compound. Its ions, those are the charged particles, they have to be free to move around. That means it's got to be either melted, so molten, or dissolved in water. If it's a solid crystal, those ions are locked in place, and they just can't move to carry a current.
We pass the electricity through the electrolyte using two electrodes. They're usually just rods made of something conductive, like graphite. Now, you really need to pay close attention here. We have the anode, which is the positive electrode, and the cathode, which is the negative one. Getting these two the right way around is absolutely essential for everything that's coming next.
And I've got a fantastic tip to make sure you never ever mix them up in an exam. Just remember the word panic. Positive anode, negative is cathode. Seriously, write it down. It's simple, it's effective, and it's a real mark saver.
Okay, we've got the key terms down, so let's see how this all actually works. Part 2, electrolysis in action. We're going to start with the simplest possible scenario, a molten ionic compound, where there's nothing else in the pot to complicate things.
Let's use molten lead bromide as our example. So first, we heat it up until it melts. This lets the positive lead ions and the negative bromide ions break free and swim around. Then, when we switch on the power, it's just a simple case of opposites attract. The positive lead ions, they get pulled towards the negative cathode. And the negative bromide ions, they head straight for the positive anode.
And this is the magic moment, right here, when the ions arrive at the electrodes. Look at the negative cathode. The positive lead ions are drawn here, and each one gains 2 electrons. This cancels out their charge, turning them back into neutral lead atoms, which then form a layer of molten metal. Meanwhile, over at the positive anode, the negative bromide ions each lose an electron. They become neutral bromine atoms, and they immediately pair up to form bromine molecules, which you'd see bubbling off as a gas.
So, that's the theory. But why is it so important? This brings us to part 3, extracting metals. You see, this process isn't just some cool lab experiment. It's a massive industrial process that we rely on for some of our most important materials.
The key rule here, it all comes down to the reactivity series. For metals that are less reactive than carbon, like iron, we can just heat their ore with carbon to get the metal out. Easy. But for metals that are above carbon in the series, like aluminium, carbon just isn't reactive enough to do the job. For these really reactive metals, we have to force the reaction using the sheer power of electrolysis.
Aluminium is the perfect example. Its ore, aluminum oxide, has an insanely high melting point. We're talking over 2,000 degrees Celsius. Trying to melt that would cost a fortune. So, industrially, they do something really clever. They dissolve it in molten cryolite. This simple trick drops the melting point all the way down to around 900 degrees, which saves a huge amount of energy and, well, money. And this brings us to a really specific detail, one that's highlighted right in the AQA specification, which is basically a giant hint that this is a classic exam question. When you're extracting aluminium, the positive electrode, the anode, it has to be replaced all the time. But why? Well, the answer is all in the chemistry. The negative oxide ions from the ore are attracted to the positive anode, which is made of carbon. When they get there, they lose electrons and form oxygen gas. But because that carbon anode is super hot, the oxygen that's just been made immediately reacts with it,
burning it away to form carbon dioxide. So the anode is literally being eaten away during the process.
Okay, so we've mastered molten electrolytes, but let's be honest, most of the time in a school lab, we just dissolve stuff in water. So what happens then? Welcome to Part 4, Rules for Aqueous Solutions. This adds an extra layer of complexity because the water itself can actually join in on the reaction.
This table right here is your essential guide. Seriously, this is gold. In a water-based solution, you've got ions from the salt, but you've also got hydrogen ions and hydroxide ions from the water itself. So you've got a competition at each electrode. Let's break it down. At the negative cathode, it's a fight between the metal ion and the hydrogen ion. The rule is simple. If the metal is more reactive than hydrogen, then hydrogen wins, and you get hydrogen gas. If the metal is less reactive, the metal wins, and it plates onto the cathode. Over at the positive anode, the rule is even simpler. If you have halide ions, that's chloride, bromide, or iodide, you'll get the halogen. If you don't have those, you will always get oxygen. Learn this table and you can solve pretty much any aqueous electrolysis problem they throw at you.
And now for our final section. Quick heads up, this is aimed at you higher-tier students. Part 5, Writing Half Equations. This is how chemists show exactly what's happening with all those electrons at each electrode.
First step, we need to be really precise about what's happening to the electrons. And this means two key terms, oxidation and reduction. The best way to remember them is with the mnemonic oil-rig. Oxidation is loss, reduction is gain, of electrons, of course. And the other crucial thing to remember is that oxidation always happens at the anode and reduction always happens at the cathode. So here's what this looks like in practice. Let's take an example from an aqueous solution. At the cathode, 2 hydrogen ions gain 2 electrons, that's reduction, to form a molecule of hydrogen gas. At the anode, 2 chloride ions lose 2 electrons, that's oxidation, to form a molecule of chlorine gas. See that little E- symbol for electrons? That's what we're tracking. And these half equations always have to be balanced for both atoms and charge.
So, let's tie this all together. The crucial point, the big takeaway, is this. Electrolysis uses electricity to force a chemical change that wouldn't happen on its own. And the products you get all depend on 2 things. First, the state of your electrolyte. Is it molten or dissolved? And second, those rules of reactivity, which decide who wins the competition at each electrode.
And that leaves us with a final thought. We've seen just how vital electrolysis is for making materials like aluminum that, well, build our modern world. But it is an incredibly energy-hungry process. As we look to the future, the really big question is, how do we balance our need for these materials with the urgent need for sustainable, low-energy solutions for our planet?